So, thank you, Melissa. So, we will have.
La 12.
Cosa ci origina sarà l'ultima.
Questa?
Sì, perfetto. Ottimo.
Okay. Melissa, the floor is yours.
Okay. Hi, everyone. Thank you for still here. Okay, still being here. Okay. I will present the last service about the soil erosion by water assessment, and it was developed by CMCC and Forest Design. So we were interested in soil erosion because it's a current huge problem. It affects several countries in the European Union and also worldwide, and is expected to worsen due to climate change. Soil erosion actually is a natural process, in theory is balanced over the long term, but actually anthropogenic activities are leading to unbalanced rates of soil loss, resulting in land degradation, food insecurity, and economic loss. Here you can see some example. As you can see, already more than half of the European Union is affected by one or more soil degradation processes, among which is soil erosion, and a quarter of the European Union suffer from unsustainable soil loss rates. And also you can see the cost that soil erosion causes to the European Union, mostly related to food production, but not only. And both ecological, environmental, and socio-economic concerns have raised the interest of policies towards this topic, and preventing soil erosion has become one of the targets of different policies recently, and they also have also started to include some soil erosion-related indicators to track the progress towards sustainable goals. And here you can see some example of indicators, and one of these is the Eurostat indicator 15.50, estimated soil erosion by water, which can be considered as a proxy or as complementary of the UN indicator about land degradation. And in this project, we were particularly interested in it because at the state of the art, its geographical features for computation are very good, but the time features like timeliness or time resolution or frequency of delivering are not satisfactory. The study site is the same of the previous service, so it's the Olte River Basin in Romania, and we decided to work in this area because of synergy for data collection and other factors with the previous service about forest cover change, and also because in this area we have a large variability of morphological and land cover land use conditions that allow us to test the soil erosion assessment tool capability in different contexts. And what we did was to provide a replicable, scalable, and open access Earth observation-based tool, also testing some artificial intelligence algorithms to improve a very widely used soil erosion model, which is the revised universal soil loss equation. Here's the team. I was, coordinating the work, but I was highly supported by some people at CMCC for the technical parts, and also by Forest Design, Mia in particular, for data collection and also for stakeholder engagement. Similarly to the other pilot and the other service of this project, we relied on a co-design approach. And we started with a collection of requirements through questionnaires at the very beginning of the projects in order to understand which features of current soil erosion assessments were of interest for the stakeholders. So in practice, what they want to know, to see. And then we produced a first demo of the service, and we presented at the first stakeholder workshop in 2024. Then we refine the project, the service according to the feedback received during the demonstration, and also the feedback during the review meeting last summer. And then we provide a new version in spring 2025, and we show it during several webinars and workshops. And stakeholders were mostly from land planning and decision makers, but in theory this service can be of interest for different sectors, ranging from research to insurance to agriculture and transport. I will go a little bit on the detail of the methodology in order to understand what the platform is offering. As I mentioned, we work on a widely used soil erosion model, which is presented here, is the revised universal soil loss equation, 𝗪𝘁𝗲, and it's an empirical model. It comprises only one equation, which is the one here reported, and it provides the soil loss as a multiplication of 5 factors. We have to notice that in this project we only consider 4 of these factors because the 5th one is generally assessed in a very arbitrary way, so it was conservative not to consider it. Interestingly, for all of these factors we found out several gaps in the computation, both through literature review and with the feedback and the interaction with the stakeholders. So we decided to deal with each of them individually. Starting from the first one, the rainfall erosivity, which is actually the driving force of the erosion process. Its computation is in theory very simple. We have a formula given by the very first handbook of the 𝗪𝘁𝗲 model. But the challenges we found out were mostly related to the fact that this formula requires 15 minutes data, so sub-hourly precipitation data, but generally we don't have this data. And also the stakeholders ask for using gridded data sets, for instance ERA 5, but also in that case the data have hourly or cursor resolutions. So we provide a different solution throughout the projects. It was also a chronological order. We started with a very simple solution. We clip and reproject an existing data set. Then we refine by implementing a new algorithm, for implementing empirical formulation to apply to hourly data, because the literature offers a lot of empirical formulations. And then we provide a more refined solution based on artificial intelligence, so we provide a data-driven neural network approach. And this algorithm was very powerful because it was able to disaggregate the hourly rainfall time series into sub-hourly. So we were able to transform, for instance, the hourly ERA 5 gridded dataset into sub-hourly and apply the rigorous formulations. And interesting, at the beginning we thought to substitute each version with the following one, but in the end we provide all of them on the platform because the new direction of soil erosion assessments is towards ensemble estimates, so we decided to keep all the 3. And the second factor is about the morphology of the territory. It's called slope length and steepness, and basically it determines how the land responds to the rainfall according to their its morphological features. And the computation in this case, it's an analysis of the digital elevation model in different steps, and the literature provides a description of each of these steps. However, in this case, the challenges are related to the fact that there is not an open source available for the entire workflow, so users cannot compute it. And the stakeholders ask for improved spatial resolution, and also they ask for the inclusion of some territorial features like transport infrastructure that actually influences this factor. So in the end, we provide a solution which is a state-of-the-art open access algorithm, and we also added an innovative, despite being simple, but innovative module for including infrastructure in the computation. The third factor is about soil erodibility, so how the textural and chemical features of the ground are able to influence the susceptibility to erosion of the soil. And also in this case, the challenges were related to the no availability of an open source code. And also in this case, stakeholders ask for improved spatial resolution, and they also ask for the inclusion of some soil dynamics, maybe related to the behavior of the soil after wildfires, for instance. And in this case, we provided one solution that was an open access empirical algorithm combining different formulation provided by the literature, and we improved the spatial resolution with respect to the Eurostat computation by changing the underlying datasets, and we use indeed the soil grids dataset. We were thinking also to a second version, so an improvement, also including some feedback from the forest cover indicator or reference to wildfires, but actually there was no time to do this, and this we are still keeping this as an idea for a follow-up project. Finally, I can talk about this factor, which was a real challenge in this project. The C factor is about land cover management, so how much the presence of vegetation and the management of vegetation, for instance, in croplands, affect the erosion process. And the literature provides a lot of methods for computing this, and for each methodology there are several advantages but also challenges. And some of the methods proposed are based on Earth observation, so we decided to go for them. And these methods generally link the C factor with NDVI or other spectral indices. And we also, with Manuela, we perform a review on all these methods, and this is currently under review. And the challenges were a lot, as you can see in this list. First, using a C factor NDVI relationship brings a lot of uncertainty. The literature provides different formulation with different results. And also changing the spectral index is challenges because every spectral index has some limitation. For instance, NDVI saturates in very dense forests or is not very good in semi-arid regions. Other indexes have other limitations, so it was difficult to choose. And we noticed that massive data were available. Let's think about all the satellite images you can have, but data-driven methods were underdeveloped. Moreover, on top of this, the stakeholders asked to improve the spatial resolution and also the temporal resolution, so they asked to go for subannual analysis to include also land use and phenological dynamics. So in the end, we provide an empirical method based on C factor and NDVI. As you can see in this map, this was quite powerful because it allowed us to perform annual comparison, for instance, the first two panels, but also subannual analysis. Here you can see Q1, winter, then spring, fall, and spring, summer, and fall, sorry. And in this way, the stakeholders were able to understand where the vulnerability increased. Reddish color means higher vulnerability, bluish lower vulnerability. So they were able to understand which area is more vulnerable and in which period of the year. So this is quite useful for land management. And in the project, as I mentioned, we also try to use satellite images and to try to test the power of artificial neural network because our idea was trying to overcome the limitation due to the use of a single spectral index by combining different spectral features. But in the end, unfortunately, the results were not so accurate, and in the end we discarded this solution. This was the risk of a research project, although we think that the underlying idea was not bad, but the issue was in the data. And here, very quick demonstration. Okay, so is it gone? Nice. Non sta andando. Io ho schiacciato play.
Allora, vediamo. Ah, aspetta, non posso vedere. Ah, ecco.
Ah, ora è andato. Ok, okay, this is how to access to the front end. So you have to click and a new panel will open. And here you can see our study area and all the panel to select the options. Obviously, the options changes according to the kind of output you want. So let's explore the output. And now you will understand why I explained everything before. Okay, started from soil erodibility. As I mentioned, in this case, we only provided one open access empirical based algorithm. So the user cannot choose anything. It can just calculate the factor. Then there's the rainfall erosivity. And in this case, we left all the free options, and the users can choose one of them and then calculate very slowly. Okay. And then there's land cover management, and as I mentioned, is a very dynamical factor, so the user can select a data, and the algorithm will define the quarter related to that date, and calculate the 𝗔 factor for that quarter. Then there's the slope, length, and steepness factor, and in this case, the user can select the options of computing with the infrastructure, railways, roads, or without infrastructures. And finally, the user can select not to see the individual factor, but just to have a soil loss map. And in that case, it has to choose all the options. So, for instance, the date, I select my birthday, 19th of April, and then the no infrastructure in this example, and the rainfall erosivity method. And then finally can calculate. Once you click on calculate, the algorithm started to run, and it can take some minutes depending on the selection of the methodology. For instance, for the artificial neural networks, it's a little bit long, so I will just show the results. In the end, you have a map, you can zoom out, you can zoom in, you have a color bar for the magnitude of soil loss, and if you click, you can see statistics, and this is how this calculation aligns with the Eurostat indicator, because we provide the area. And you can also download and save your result. So that's all. Okay. Okay, and very quickly, we also, I stress a lot the fact that we provide an open access tool, and this was because it was very critical, the fact that there was nothing available for soil erosion, and also the, the available estimation of soil erosion as, available estimation of soil erosion are not based on open access or replicable workflow, and I think this is not very fair. So we decided to keep everything open, and the users can also use the backend and explore the algorithm we wrote. And as you can see in this panel, we organized the backend following the 𝗪𝘁𝗲 formulation. So we have a main, which is an orchestrator, and then for each factor we have a specific module. So the modules are called at the beginning after the libraries, and then you can select the options, very similar to the left panel of the front end. And then the algorithm will check in the folders if some outputs for your options are already available in order to avoid the double computation. And then it will start to compute each factors. So it called the first one, then it called the R, the K, and the 𝗔 factor, and finally reproject everything and compute the soil loss. In this notebook, you can also export the file as a raster, so in a TIFF format, and you can also plot the results. To conclude, just an overview of the challenges. As I mentioned at the very beginning, the features of soil loss by water at the European level was not very satisfactory regarding the 10 features, and here you can see the Eurostat grading systems. And by using new Earth observation data, and by using also by providing also open access algorithm, we were able to improve all of these features, so we were quite satisfied of that. And regarding transferability and upscaling, we designed the workflow and we selected the data in a way that the solution can be transferable and upscaled. And as you can see here, we use a lot of data sets that have a very large geographical coverage, and we use some specific local data set that, however, can be replaced. For instance, we used the infrastructure shape files for roads and railways provided by the geoportal of Romania. But actually, if you want to apply the codes elsewhere, you can rely on OpenStreetMap. So we have a replacement ad hoc replacement for each local data set. And regarding always the same topic, although we don't have issues related to the data, we found out some issues in scalability related to the resources required. So if you want to apply the artificial neural network for the computation of the R factor, or if you want to compute the C factor or the LS for a very large area, you have to account for the computational issue because the code is quite demanding. However, for the R factor and the C factor, you can work on parallelization because the factors are not spatially dependent, so you can split and compute. While for the LS factor, we are still working on optimization in sister projects because it's spatially dependent. It depends on the watershed features, so it's not so easy to speed up this computation. Regarding exploitation and sustainability, we provide a different kind of service and products in this project. So you saw the tool, you saw the algorithm, and you saw the datasets. And we also perform several dissemination activities in conferences with posters and oral presentation. And as I mentioned, we have one publication under review and other under preparation. And we also thought about potential uptakers, which corresponds to the potential stakeholders I mentioned at the beginning, so researcher, insurance, but we also thought about the national statistic offices or NGOs. For instance, during the last webinars, there was some representative from, I think, African NGOs that were interested in the service. And we also thought that the data sets or the service can be included in the 𝗘𝗿𝗃𝗀𝗃 service, both in the catalog or as a demonstrator. And we did something similar to SDGs-EYES in the past with a soil erosion demonstrator in Italy, and it was very, a very basic version, so we think that this improved version can be of interest. So that's all, and thank you for your attention.
Thank you, Melissa. Question for Melissa. I have one comment, but okay, Thomas, because I know well. Thomas, go.
Thanks, Melissa. Actually, it's more a comment. I was just wondering, since you have all the land cover maps and all the information about the type of territory that is over or together with your soil, and thinking to your first slide about the cost of all these soil losses, I was just wondering if it could be an idea to try to put a sort of an economical value or an economical yield associated to each land unit or land type, and then link this information together with the soil loss so that the tool will provide also a potential estimates of the losses that you're going to experience. So you combine the information in a way. I mean, it's just
thank you. This is interesting. Yeah, thank you. Yeah. We can actually, it's not so difficult to implement.
No, basically, no,
if you
because
have the data.
Yeah, it's, you need to find out which is maybe from agriculture portal or some a statistical portal from European Commission. Yeah. There are like also price of the economical value of it. Yeah, we didn't think about that. Could be really, of course, interesting to translate, to managers and to see which is also the economical loss. The economical loss, it could be also evaluated in another way, in maybe if you put like productivity map for some period. There are also from Copernicus. This is the real, for instance, loss of grain biomass in terms of real of biomass, but also this one, it's very interesting because you evaluate how many land you lose. Yeah, we need to think about it in the next day or so. We have to review. Yeah, thank you very much. No,
but it's interesting. It works.
It's I had also another question because we are talking about soil erosion by water, and it came in my mind that this area east of Europe some years ago had a very strong storm and windstorm, and I was thinking, okay, was extreme climate, but in Mediterranean area, when we have a poor vegetation, how the wind wind erosion can affect or add to the erosion by water.
Yeah,
maybe.
wind erosion it has always been an interest of CMCC, but never been explored so much because the models are different. But once you have the the space for the data set and the computational power for computing, I think you can just combine.
Or
so
maybe
it could be
yeah.
feasible.
I was thinking also to the pilot on Sahel region with droughts. Okay, it's true that here we have rain, the effect of rain, but basically it's the effect of raindrops on the surface, but it doesn't take into account which is the droughts of the land. So maybe also this could be okay for another project, not
it's
for.
a pity that the project is finishing actually, because now that the pilots are ready, maybe synergies could have been interesting, but it's finished. Okay.
Other comments? Or? Okay.
Okay, perfect.
Thank you very much, Melissa.